Okay, so we'll go ahead and get started. It's 12 o'clock. First thing I'm going to mention this, there'll be a few flyers put up around the department. In an attempt to entice students towards physics, they're offering a free pizza lunch. So if you'd like to drop by and just sort of see some other physics students and faculty, maybe hear a little bit about the kind of things that's done in our department, you might enjoy this. So that's Wednesday, day after tomorrow, in room 2039. That's the small lab out there. So if you're interested, you are warmly welcomed. The tests I gave back to you, I'm trying to remember, I don't know if this applies to anybody here. A lot of people misinterpreted 4A. So I asked you to show, let's see if I have a question here. I asked you to show, oh, I don't have a blank copy, I don't want to put up anybody's test. I asked you to show how the Biot-Savart law can be applied to a wire to find the expression that's given on the test in part 4A. I was asking you to derive that result, and that was something we had done in class. But it seemed to be misinterpreted. A lot of people thought I was asking for the magnetic field around a long straight wire, but that was not the question. And I went back and forth, kind of what's the best way to deal with a misunderstanding. And in the end, I just kind of put 5 points on top of everybody's grade, because I know if you misinterpret a question, it can throw you off your game and impact the rest of the test. So I kind of thought that was the most fair way to deal with it. So your grade on your test, it had 5 points added onto it. So there's that. Okay, so any questions before we start? No, we're good. So last day we talked about magnetic fields around loops, and we introduced Ampere's law. We're going to pick up there today. And we're going to do something with Ampere's law, very similar to what we did with Gauss's law. And when we use Gauss's law to find electric fields inside and outside of solid objects. We're going to do the same thing. We're going to use Ampere's law to find the magnetic field inside of a solid conducting cylinder. So imagine if you had something like this made of solid aluminum. We run some current through it. How do you find the field inside and outside? So we've got this long solid cylinder. It has charge in it. The charges are moving, so there is a current. So let's draw the charges on our wire. So they're going down like this. So there is current flowing. These moving charges are the current. We'd like to use Ampere's law. So as a reminder, Ampere's law says that the integral, we put a circle on it to tell us that it's around a closed path of the magnetic field dotted with an element of the path is equal to mu naught times the current enclosed by that path. So there's our Ampere's law. Our wire has radius r, so we can put that on the picture. So from the center to the outer perimeter is the radius of the wire r. And we're told that it has uniform current density J. Current density J is the current that passes through some area on the face. It's a circular wire, so the area would be the area of the circle. Equals I over pi r squared. That's our current density. I equals total current flowing through wire. So there's our setup. We want to find the magnetic field inside and outside. Let's start with inside. So if we want to apply Ampere's law, we have to pick a path, and we're going to do the integral around that path. What path are we going to pick? We want it to reflect the magnetic field. We know the magnetic field around wires is circles, so our path should be a circle. So that it reflects the symmetry of the magnetic field. And it should have a radius less than the radius of the wire so that we stay inside the wire. So let's draw our path. So there's my total path S. It's got a radius of R. And we might like to put some direction ds on there, so let's identify the little bit of our path, ds. ds is a vector, it has a direction. If my current goes this way, my magnetic field lines are coming around this way. So in the front, my ds is pointing down because that's the direction of my magnetic field. So I'm picking ds to be parallel to the magnetic field. Okay, so let's write down our Ampere's law. So it's got two sides, integral of b dot ds, and it's got mu naught times the current inside. So b dot ds equals mu naught times I inside. Let's deal with this side first, the integral of b dot ds. We did this last time, but it feels like a million years ago, so let's just kind of go through this one again quickly now. The integral of b dot ds is equal to the integral of b times ds times the cosine of the angle between b and ds. We set out to make our b and our ds parallel, so the angle between them is 0. So b times magnitude of b times the magnitude of ds times the cosine of 0. So that's the integral of b times ds. As long as we're a constant distance away from the center, that b is going to be constant. It comes out in front of the integral. So now I've got b times the integral of ds. The integral of ds is just the path length. And since our path is a circle, our path length is the circumference of the circle. So that's b times 2 times pi times r. Any other example like this we do in class today, I'll go from here to here, and I'll write down show steps. This is what I mean by the steps. So on a test, you would have to show that part. The other part that we need to put in our equation is what is I in. So I in equals current enclosed by the path. So our path only encloses a part of the total wire, so we only have part of the total current. If we want to find the amount of current, we can use our idea of current density. Current is density times area. So to get the current enclosed by the path, we'll do the current density, which we know, and multiply it by the area enclosed by that path. Our current density is J. The area of our path is pi r squared. J is our total current I divided by pi times the radius of the wire squared. That's multiplied by pi times little r squared. Pi's cancel. So our IN, the current enclosed by the path, is our total current times r squared over r squared. So the current enclosed by the path is just a fraction of the total current. It doesn't enclose all of the current. Okay, any questions about any of those bits and pieces? Okay. So let's come back to our Ampere's law. Let's put in the things that we just figured out. So the integral of b dot ds is b times 2 times pi times r. Mu naught times I inside is I times r squared over r squared. We want to solve for our magnetic field. B is mu naught over 2 pi times I times r divided by r squared. So there's our magnetic field inside the wire. We know it circles. We know the orientation is given by our right-hand rule. Put our thumb in the direction of current and it comes down into front. So we get our direction of the magnetic field using the right-hand rule. Okay, any questions? So that's inside. We'd also like to find the magnetic field outside the wire. So for outside the wire, we'll do the process again. So outside. Let's draw our wire again. So here's our wire. If we'd like to find the magnetic field outside, we'll follow the same process, but this time our path needs to reflect the magnetic field, so it should be a circle, parallel to the magnetic field B. And we should have a radius outside the wire, R greater than R. So let's draw the path. So there's our path S. A little bit of the path would be ds. It's got a radius of little r, and the radius of our wire is big R. Okay, so there's a diagram like we had in the first part. If this were a test and you drew this path on this figure, that would be fine, as long as it's clear and I can see it. But if you don't like it to get too messy, a second diagram is not a bad idea. We're going to apply our Ampere's law. Integral of B dot ds equals mu naught times I n. We need to sort out both sides of the equation. So for this part, we will say show steps. And it equals to B times 2 pi r. Again, if this were a test problem and you had to do A and B inside then outside, for here you could say follow the same steps done before, right? You wouldn't have to write out all the same steps in the same problem. So show the steps, we know B equals 2 pi r. For our I inside, sometimes it is tempting to use this expression again, just like it was in Gauss's law, that the current enclosed by the path would be the density times the area, which would give you this same expression, but it wouldn't exactly be true, right? The only thing with current inside of our path is the wire. So the only current inside is the current of the wire. It equals I. If you tried to use this equation, but your little r was bigger than the radius of the wire, your I inside would be more than the total current in the wire, and that doesn't make any sense, right? The maximum current you could have would be the current of the wire. Okay, now we put it together. B times 2 pi r equals mu naught times I. B is mu naught over 2 pi times I over r. We get the direction using the right-hand rule. Okay, so there's our magnetic field inside and outside of a solid conducting cylinder. For inside, we saw it was proportional to the radius, so it was linear here. And out here it falls off as 1 over r. You might notice that once we're outside this solid wire, it looks exactly the same as for a thin wire. So once you're outside of an object, the electric and magnetic fields don't care about the object itself. Okay, so once you're outside, you can't tell if it was thin or if it was thick. Okay, the next thing we'll do is we'll graph our relationship. So plot the magnetic field of a wire of radius r with a uniform current density. So that's the problem we just solved. Let's just put our equations here on this page. So inside the wire, r less than r, magnetic field was mu naught I times r over 2 pi r squared. Outside, r greater than r. Magnetic field was mu naught I over 2 pi So for our graph, the interesting point is going to be right at our equals bar. Inside it's linear, it increases with respect to r. So here is inside. It's linear. And outside it falls off as 1 over r. And so it goes to 0 once we're further away. An interesting place on our graph would be what happens at r equals r. Well, at that point, b is mu naught times I times r over 2 pi r squared equals mu naught times I over 2 pi r. Okay, so there's our maximum field right here. Okay, any questions? So the next one, I think this is kind of an interesting application, would be a coaxial cable. Anybody who's kind of into electronics a little bit probably has some cables lying around their house. In a coaxial cable, you got 2 wires. There's one going down the center, and there's one on the outside. Let's see them. I got these out of a bunch of garbage that the IT guys were throwing away. If you're still listening, right? There's a thin wire down the center, and there's a wire around the outside. They make it like this on purpose, and it has a really important impact. So what we're going to do is, we know when we run current through the wire, it's going to make a magnetic field. As we're getting started here, we might start to think about, we have cables, especially when you hook up computers, right? So most computers have got a bunch of cables in there somewhere, and other electronics. If the current carrying wires create magnetic fields, what does that do to your electronics, right? So you always want to shield them from electric and magnetic fields. So what about these current going through all these wires? So let's have a look at that and talk about the field of a coaxial cable. So we've got a solid conductor with radius A, that's on the inside, that's the skinny wire you could see, supported by insulating discs. So all that means is that we need something to hold those two things in place. Usually they're like little ceramic pins, so they keep that middle wire in place. The tube is the wire on the outside, that carries current. It's got a radius inside of B, outside of C, so it has a distinct thickness. The central conductor and the tube have equal currents, but in opposite directions. Okay, so that's the big deal about these coaxial cables. They carry the same current, but it flows in opposite directions. Currents is evenly distributed, that means our current density is uniform. Find the magnetic field inside the cavity here and outside the whole thing. Okay, so that's a good thing to try and figure out. So for part A, we're going inside the cavity. So R is between A and B. So A less than R less than B. Let's draw that path. So we're following more or less the same process that we did in that previous example with the solid wire. So we'll go just a little bit faster. So here's our path. It's got radius R. The current is coming this way, so we'll do a little bit of our path, ds, so that ds matches the magnetic field, ds. We want to apply, this is in the cavity. We'd like to apply our Ampere's law, integral of B dot ds equals mu naught I in. So let's see what we're going to do here. Our path equals circle with a radius A less than R less than B. And the orientation matches the orientation of the magnetic field. So for this side of the equation, we will say show steps. Our result will be that it's equal to B times 2 times pi times R. current inside is the current enclosed by this path. That is the current I that travels through this wire. So this is basically exactly what we did looking at the magnetic field around that solid conductor. So when we put these things together, we get that the magnetic field times 2 times pi times r equals mu naught times I. B equals mu naught times I, 2 pi r, the direction given by the right-hand rule. So when we had Gauss's law, we really stressed that the only charges that mattered were the charges inside. Same deal is true with Ampere's law. The only current that matters is the current inside the path. The fact that this outer shell has a current does not affect the magnetic field inside that cavity. It's only the currents inside the path that count. Okay, so that's an important part to notice here. We also want to find the magnetic field once we're outside the tube. So part B, we're outside, so we're R greater than C. Let's draw another path. So this time I'm going to draw a path that's outside the whole thing. That's got radius r. And our ds, we have to pick a direction. I'm just going to pick the same direction that I had before, ds. I'll write my Ampere's law. The integral of b dot ds equals mu naught times I in. Okay, I'm going to do my I in first instead of my integral first. So my I in equals my net current enclosed by my path. So my I in equals a current I minus current I. They flow in opposite directions. So my net current here is actually 0. So current I this way, current I that way, total current, because you remember currents are really vectors, total current is equal to 0. So the result is that outside the coaxial cable, B equals 0. That's why they use coaxial cables. You send high current through it, you get high magnetic fields, it messes with your electronics. Okay, so that's why we use these sorts of cables. Okay, questions? So, let's do another application of current carrying wires. Your book has more applications. I'm only going to do the solenoid. If you're interested, you can look at the other ones. They are interesting, but we do have very limited time. So, the application we'll look at is a solenoid. So when we have a long straight wire, we know that putting current through it makes a magnetic field around it. We can take our wire and we can coil it up. What you get is something that looks like this. Okay, so a slinky could be thought of as a solenoid. We typically do this lab in physics 1051. We run current through a slinky, you measure the magnetic field in the center. So what we find when we have a solenoid, and there's our definition of a solenoid, a coil of wire with the same current passing through each loop of the coil. When we run current through it, we get a magnetic field. So we're running current through, it says it's coming up in the back, so it's coming down in the front, comes out through the front. What we find is that if we have an ideal solenoid, and this picture is meant to imply an ideal solenoid. This would be something that's infinitely long. For an ideal solenoid, the magnetic field is inside the solenoid. It's completely uniform along the length, and the magnetic field outside is 0. So uniform inside, 0 outside. So that's an ideal solenoid. This is the one we're going to look at with the theory. It's probably good to know that, of course, most things aren't ideal. They're more realistic. So a real solenoid would look something like this. It's got some space between the coils, and it's not infinitely long. You know, it's yay long or whatever. And most real solenoids are like that. When we have a real solenoid, we still get the biggest magnetic field through the center. So it still comes down like this. It's big in there, but it's not entirely constant. Once we get to the end, we get some variation. And it's not completely zero outside. It kind of curves around a bit outside. So that's what it would look like in a real solenoid, and we're going to stick with the ideal ones, where it's constant and uniform inside and zero outside. So let's apply Ampere's law, and let's figure out how we find the magnetic field inside of a solenoid. So the first thing I'll do is draw my magnetic field lines inside that solenoid. We are assuming an ideal solenoid here. We're not going to try and figure out all those edge effects for a real solenoid. So here's our magnetic field. It's uniform inside. There's our B. Getting the direction of the B, if you put your thumb in the direction of current, so it's coming up in the back. Your curled fingers show the magnetic field. So there's the solenoid, looking like this. The current comes up in the back, right? So my thumb is going up in the back. Your curled fingers are pointing in the direction of the magnetic field, which is that way. Okay, so I'm looking at the back of the wire, My thumb goes up in the back here. Circle with my fingers, show that the magnetic field points this way out of the end. So that's how you get the direction. You still use the right hand rule. You can also kind of flip that right hand rule. If you make a circle with your fingers to represent the current, your thumb shows the magnetic field. It works both ways. So your fingers come up around like this and the magnetic field comes out like that. So we're going to apply Ampere's law. The integral of B dot ds equals mu naught times I inside our path. This time the path is a little bit trickier, so we need to pick some closed loop. It definitely has to be a closed loop. When we did a wire, we knew that the magnetic field made circles, so we had to pick it making circles around the wire. This is not so simple. Here the magnetic field looks like this here, and we want to pick a useful path. So for a useful path, what we could actually pick is a loop, a rectangular loop, where part of the loop is inside and part of the loop is outside. So if I draw a rectangle that comes down here, up here, like this. I have to put a direction on my loop. On the bottom, I'm going to make it match the magnetic field. So it's going up on the right, left on the top, down on the left. This path matches the magnetic field inside, but we also know some stuff on the sides, and we also know some stuff on the top. So I have lots of information about this path, even though it doesn't exactly match. So my path is a rectangular loop. Partially inside and partially outside. If I want to find my net integral of the magnetic field around the path, what I'll do is B dot ds for each of the 4 bits and then add them up to get the total. So I've got 4 pieces of the path. So I want to do B dot ds for each part. So I'll call the top bit segment 1. So up here will be 1. So on 1, the integral of B dot ds is the integral of 0 dot ds equals 0. remember we said that the magnetic field outside the solenoid was 0. So everywhere along this length 1, B is equal to 0, so the integral is equal to 0. Okay, then we come to part 2. That's the bit that comes down. The integral of B dot ds is equal to the integral of B times ds times the cosine of the angle between B and ds. So on path 2, ds points down, magnetic field points right. That angle is 90 degrees. So the integral of B dot ds along path 2 is equal to 90. Let's skip ahead and do path 4 on the other side. That's the same, B ds times cosine 90 equals 0. So still at a right angle over there on path 4. And then we have path 3. That'll be our last bit down here. On path 3, integral of B dot ds is the integral of B times ds times cosine of 0. Those two are parallel. ds is to the right, B is to the right. So I've got the integral of B times ds. B is constant everywhere inside that solenoid, so take B outside. Integral of ds is the length of this path. I'm going to call that a lowercase l. So integral of ds would be the length. So everybody good with that bit? So now we'll add up the 4 to give us the total integral of B dot ds. So then the net integral around that closed path, B dot ds, 0 plus 0 plus 0 plus B times L, whatever the length of that path was that we chose. The other side of our equation deals with the current inside of our closed path. So let's think about what that current is equal to. I'm going to zoom in on my picture again. So in our coil, the current comes up in the back, which means it comes out front towards us at the top of the loop. So everywhere on the top of this loop, the current is coming towards us. And then it goes down in the front and it goes away from us on the back. Everybody okay with that idea? The current comes up and back, so it's towards us at the top. So the net amount of current enclosed by this specific loop is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times the current, right? So I've got 11 coils inside here. Every coil has current I, so my total current is 11 times the current I. That's for this specific loop. I'd like to say a little bit more general. My current inside my closed path is the number of coils, or the number of loops, times my current I. I'm going to call number of coils N. Okay, so my specific one was 11. It could have been any. So let's put everything together. These two things have to be equal. So B times L equals N times mu naught times N times I. So my magnetic field inside of a solenoid is mu naught times N times I divided by the length. This is one expression. This is valid. This one is used quite a bit. Sometimes, however, with solenoids, you don't want to count up those numbers of loops because there could be thousands and tens of thousands of them. So often we'll define a lowercase n, total number of coils divided by the length of the solenoid, and that's called coil density. So most often we say for solenoid, B is equal to mu naught times the coil density times the current with the direction given by the right hand rule. Okay, so that's how we find the magnetic field inside of a solenoid. Questions? Okay. So definitely got time for some examples. example of a solenoid, probably most people have heard of, would be an MRI machine. So maybe you've had an MRI before, somebody in your family, probably you know of someone who's had a solenoid. That's all this is, right? This big machine, this big tube, that's got thousands and thousands of coils inside here. They run a current through the coil, it makes a magnetic field. Your body is full of magnetic fields. Those interacts, they read the interactions, and that's how they read an MRI. So we've got a 1 meter long MRI. It's got a 1.2 Tesla magnetic field. That's a pretty big field. So it's wrapped up with wire that can carry 100 amp current. How many turns of wires do we have to have? So we're looking for N. So the length of our solenoid is 1 meter. The magnetic field at the center is 1.2 Teslas. The current we're running through it is enormous, that's 100 amps. And how many coils do we have? So B is mu naught times N times I, mu naught times N times I over L. So N is going to be the magnetic field times the length divided by mu naught times I. So about 9,500 coils. Anybody see any complications with trying to coil 10,000 coils of wire? That's got finite thickness, right? So a wire certainly has some amount of thickness. 10,000 times anything is pretty big. So this can lead probably longer than a meter if you had to coil them all together like a slinky. So if it was all single coils bunched up like this, it would probably get too big because they all have to be plastic coated, right? It can't touch. So what they do is they do one coil and then they go on top and on top and on top. You have multiple layers. You think there's any concerns about running 100 amps through it? That's a really high current, right? The reason they use superconducting wires is so it doesn't get so hot. Right? So you want to tinker with the resistance, which we can do using a superconductor, so that we're not throwing off loads and loads of heat. We wouldn't like our MRIs to catch on fire when you go in to get one done. So lots of stuff there. So another example, still kind of plug and chug. A solenoid is 35 centimeters long. Make a list of the things that we know. Length is 0.350 meters. Contains 450 circular coils, so that's our capital N. 2 centimeters in diameter, so the diameter D is 2 centimeters. If we carry the radius is half of that at 1 centimeter. Carries a current of 1.75 amps. Part A, what is the magnetic field at the center of the solenoid? So 1 centimeter from the coils. So for part A, we'll use our expression. B is mu naught times N times I divided by the length. Put our numbers in. So the magnetic field at the center of that solenoid would be 2.83 times 10 to the minus 3 Teslas. If we wanted to put a direction in there, so we could make our current carrying wire look like this. If the current went up here in the back, then our magnetic field would point to the left. Okay, so from this end of the solenoid, it goes up in the front. Your fingers curl with your current, your thumb shows your magnetic field. But we'll just remind ourselves in general that we can find the direction with the right-hand rule. So now this might be a slightly interesting comparison. What if we take our coils and we stretch our solenoid? So we take our slinky and we stretch it, we uncoil it, so now it's a long wire. What would the magnetic field 1 centimeter away from the wire be? And do you think it should be the same or should it be different? So for part B, we take our solenoid, we stretch it out, and try and find the magnetic field, the distance of 1 centimeter away. So this would be the case of the magnetic field around a long straight wire, mu naught times I over 2 pi r. Put our numbers in. This magnetic field turns out to be 3.5 times 10 to the minus 5 Teslas. Do we get the same answer as A? Definitely not. Why or why not? Well, I would say we shouldn't possibly get the same answer, right? It's not the same thing. A bunch of wires tightly packed in a coil is just different than one long straight wire. So it makes sense not to get the same current because they're different things. So then the last example we'll do is one of my favorite examples, and it leads us into talking about permanent examples. If we think about a hydrogen atom, it's got a proton at the center and it's got an electron whipping around it. If we think about what's happening here, an electron is charged and it's moving. That's kind of the same thing as a current, right? So moving charge is current. Atoms effectively can be thought of as having current because it has moving charges along a well-defined path. So we're going to talk about it like that. So that's part A. What is the effective current due to the electron motion? And we're going to say that the electron is moving around according to these arrows. So here's the velocity of our electron. So for part A, we know that current is charge over time. The charge is the charge of an electron minus the fundamental charge. Time, we don't exactly have time, but we could sort of think about it. So the velocity of our electron would be distance over time. If we think about one cycle, one revolution, the distance would be a circumference, 2 pi r, and that would take some amount of time, delta t. So our time delta t is 2 pi r divided by the velocity. Okay, so that's how long it takes to go around a circle once. So our current would be minus E over 2 pi r over V equals minus E times V over 2 pi r. So our current is minus 1.6 times 10 to the minus 19 coulombs. The velocity, 2,200 kilometers per second, 2,200 times 10 to the 3 meters per second, divided by 2 times pi. The radius is 53 picometers, that means times 10 to the minus 12 meters. Gives us a current of minus 1.06 times 10 to the minus 3 amps. The negative sign just implies that it's opposite the direction of the velocity. So if our electron comes this way, the current goes in the opposite direction. This is a pretty big current, right? That's 100 milliamps. That's a large current. So I think that's kind of interesting. So that electron whizzing around makes a big current. What is the magnetic field at the proton due to the electron's motion? So the electron is moving around. It's a moving charge. It creates a magnetic field, right? So moving charges make fields. So for part B, we'll use the Biot-Savart law. Magnetic field created by a moving charge is mu naught over 4 pi times Q times V cross r hat divided by r squared. So V cross r hat, r is towards the nucleus. So R hat is towards the nucleus. R hat points this way. To get V cross R hat, we'll do our right-hand rule. So V is this way, R hat is this way. So our magnetic field would point down. That would be for a positive charge. Our electron is negative, so it has to point up. So you go V cross R hat to get V pointing down, but it has to point up instead. Alternatively, you make your circle with your fingers representing your current. You see that your B points up with your thumb. So different ways to do the same thing. So B overall is going to point up. So the magnitude of our field B is mu naught over 4 pi times the magnitude of our charge times the magnitude of the velocity times the magnitude of R hat times sine of the angle between them, which is 90 degrees, divided by R squared. So that's our fundamental charge. V is 2200 times 10 to the 3 meters per second. R is 53 times 10 to the minus 12 meters. So our magnetic field that we get is 12.5 Teslas. And it points straight up. And we got that direction with the right hand rule. So that's a very big magnetic field, right? Most magnetic fields are teeny tiny, 10 to the minus 3, 10 to the minus 5. So that's a big field created by that moving electron. Part C, what is the magnetic moment of the hydrogen atom? So here's where we remember the definition of magnetic moment. So part C, magnetic moment is current times area. So that's going to be current times pi times R squared. We found the current in A, and we know our radius. So our current was 1.06 times 10 to the minus 3 amps. R is our 53 times 10 to the minus 12 meters. So our magnetic moment is 9.35 times 10 to the minus 24 Teslas times meters squared. We said that to find the direction of magnetic moment, you curl your fingers with I, your thumb shows your moment, so that points straight up. So there's the magnetic moment. So every hydrogen atom basically has this magnetic moment. It's got that field and this moment. What happens if you place the atom in an external field? Here's where we would remember torque equals mu cross B. And typically that would tend to make it spin or rotate. Okay, so there would be a non-zero torque, and torque just causes things to spin. Implications of this. So this is every single hydrogen atom. So this is all of them. And not just hydrogen atoms, it's all of the atoms, because they all have electrons whizzing around the nucleus. So all of the atoms you can think about do this. And this is where magnetic materials come from. Okay, this is why a permanent magnet is a permanent magnet. So when we have our atoms, you have the electrons move. So the electrons, they orbit, makes a magnetic moment. Electrons not only go around in a circle around the nucleus, they also spin around in circles. So they also spin. That makes another U, which is actually called spin. In most materials, all of those things are random, so they don't all line up. So in most materials, non-magnetic materials, they're all random and it all cancels and it's not a magnet. In some materials, those are called ferromagnetic. In some materials, all those little mu values, they all line up. So I think that's really interesting. So in some materials, they all point in the same direction. That's what happens in permanent magnets, and that's why a magnet is a magnet. So I think that's really cool that when your fridge magnet sticks to your fridge, you're seeing the electron motion and the way all the atoms are aligned. So I think that's pretty neat. Okay, so that leaves chapter 28. Chapter 28 is done now. We'll start chapter 29 and we'll see how far we get. We only have, 5 classes left, 6 classes left. I'm considering, I know the last day of classes, Monday, April the 10th, we're supposed to have a lecture. I'm sort of thinking about skipping it because it's so close to final exams. So let me know your feedback, like if you're in favor of skipping it. Well, actually, show of hands, who would rather skip it and or have an optional review? And who would prefer to do brand new material that you'll be tested on 3 days later? Yeah, okay, it's kind of what I thought. Okay, so we'll probably lean towards canceling that lecture in favor of a possible review session.